Hello, I'm glad to give this talk for the International Workshop on Real and Complex Singularities, and many thanks to the organizers for giving me the opportunity to speak here. So let's start. I will, let's see, yeah. I will speak about the trivialization of equi-resolvable families of isolated singularities. And I will try to find the differentiable enough trivialization. Yes, so maybe r times differentiable with continuous derivatives, or maybe even with Lipschitz derivatives. So let's see, let's begin. Let's start from the very basic. Consider a hypersurface germ. Yes, the germ inside Cn, defined by some complex analytic equation, some power series, with an isolated singularity. And take a deformation. So t is the time here, and we deform by some higher order terms, as always. And then for any small value of t, we have the germ of a hypersurface, again inside Cn. Yes, we always consider everything centered at the origin. We assume that the singularity remains at the origin. And the question is, when is this family topologically equisingular? As the time changes slightly near the origin, when does it remain topologically equisingular? Well, more precisely, we want a homeomorphism that is supposed to act fiber-wise. Yes, so it sends the product of two germs to the product of two germs, and here how it acts. X and t goes to pt of x and t. So the homeomorphism is identity on the second variable. And the most important thing is the first coordinate. And here, phi t is the trivializing homeomorphism. Yes, it is some automorphism of the germ of Cn. It must depend continuously on t. And what it should do is it should send the initial member of the family, yes, the initial hypersurface, to the deformed hypersurface. So this is the trivialization. And the effect of life is that in many cases, this phi of t cannot be chosen differentiable. So it is genuine homeomorphism, and we cannot do better, much better. Yes, the problem is always at the origin. So let's recall the classical example. Take the simplest possible function. Yes, this defines an ordinary multiple point in the curve in the plane. Yeah, so here we have four smooth branches, pairwise non-tangent, a very simple singularity. Now, a diffeomorphism of the plane germ must induce a C-linear map on the tangent space, yes, by the derivative, by the complex derivative. And then this linear map will act also on the projectivization, which is P1. But any such map must preserve the cross ratio of 4 points on P1, which means the cross ratio of the tangents to the branches of this curve singularity. And therefore, if we perturb the initial f by some generic homogeneous polynomial of degree 4, then the family is not differentiably trivializable. Of course, it is continuously trivializable, even Lipschitz trivializable, but not differentiable. Well, so let me recall the classical approach to construct the topological trivialization. So once again, we need this homeomorphism, and especially this phi t of x. And the standard way is to produce such a trivialization is by vector fields and ordinary differential equations. So one begins with this equation. Yes, here we have the derivative of f with respect to the time. Rho is called the control function, and this xi is a vector field. Yes, and if we manage to find the continuous solution to this equation, then we manage to find a homeomorphism that will do the job. And this is very old story, yes, with the key work of Damon Gaffney, and then many other people developed this and applied to various in various setups, to various cases. Now, in some cases, if you have a good choice of this control function and this vector field, then one can ensure that the homeomorphism is actually by Lipschitz at the origin, or even CR. And I will give a very brief report on trivializations constructed without using the ordinary differential equations. It appears that one can trivialize differently. So let me start with a very simple observation, with just for plane curve singularities. So consider a family of plane curve singularities. So we start from some particular germ. Here is a plane curve singularity, and then we deform it. Yes, we embed it into the family. This is the family of plane curve singularities. Yes, this is the base. The base is one-dimensional, smooth, and this is our central fiber of the family. And the family is embedded into the product of the germ of the plane times the germ of the base. Yes, and each fiber of the family is defined by the deformed equation, as always. So this is the zero locus of f plus t times the perturbation. And now what I will do, let's take the trivialized neighborhood of the central fiber, yes, of the initial member of the family. The Tubule neighborhood, and we trivialize it, at least in the C infinity way. Actually, we can do it even real analytically. And as we trivialize it, we get the disk bundle. So for each point of this solid black curve, we have some sort of normal slice, yes, the blue slices, and they project onto this black curve. And we can invert this projection in some sense. So we start from some point x0, and then we can move inside this fiber, the fiber of the C of this projection. So, and we move in the very natural way. X0 goes to x that depends on x0, of course, and the time. Yes, and this this point is defined as the intersection of the fiber of the tubular neighborhood with the member of our family at the time t. Now, what is important is that this function, yes, this coordinates as a function of t and x0 is determined by the implicit function theorem. And we don't need here any ODEs, yes, just the implicit function theorem. And therefore, we can define, if we start with the R-analytic trivialization of the tubular neighborhood, then we can define the R-analytic trivialization of our family as follows. So we start from some x, yes, which sits inside in the intersection. Oh, it should be x0 here. Sits inside the intersection of the fiber of the tubular neighborhood and some member of our family at time t prime. And it goes to, well, again, the same fiber and the shifted member. Yes, the member at the time t plus t prime. In this way, we define this homeomorphism, which on the tubular neighborhood is just even R-analytic. Now, this should be slightly adjusted because you see we have here t plus t prime, so very quickly we get out of the tubular neighborhood. So this should be slightly adjusted at the boundary by some bump functions. And then we should extend it to the origin, to the whole germ of C2. And then we get a trivialization. So we have constructed here the trivialization of our family, and we did not use any ODEs here. So the question is, can this idea be generalized to higher dimensions and codimensions? And the answer is yes. So this is what I will speak about. Let's start with the preparations. So take a reduced germ with isolated singularity. Here it is. Now f is not just one equation, we have several equations, therefore I draw here the underline to emphasize that it is not a hypersurface. It is not necessarily a complete intersection, not necessarily pure dimensional, just a reduced germ, and the singularity is isolated. And take the embedded resolution. Here it is. As always, we start to blow up our germ of Cn at the origin, and then we reach at some resolved space, blown up space, Cn, and we have the exceptional divisor. It is reducible usually, consists of many reducible components. And our hypersurface, our singular germ lifts to the strict transform. And once again, so pi is the composition of blow-ups at smooth centers, as traditionally is taken for the resolution. And E is the exceptional divisor. It is the union of its irreducible components. And we assume that this is a normal crossing divisor. And the strict transform is smooth. And moreover, it intersects the exceptional divisor transversely. This intersection is transversal. The standard conditions for the resolution. Now take a deformation of our germ by some higher order terms. Yes, as always, here T belongs to C1. It is one parameter family, linear family. And assume that this family is pi-resolvable, which means each strict transform is smooth for T small, and the strict transforms form a locally trivial deformation of this initial member of the family, of the central fiber. It's strict transform, yes. And then we want to trivialize our family, which means, I repeat, to provide such a continuous map, yes, that restricts onto homeomorphisms for each value of T here, and it sends the central member of the family, central fiber, to the fiber at the time T. Well, and we want to do this locally near the family. We do not want to perturb the whole space Cn. We want to shift the points only near our family. Well, let's start with the full space, the space of the family. Yes, it is the union of all the members, as T is small. T0 is some fixed small number. So here we have the disk of radius T0, and we just take the union of all these germs, and we erase the origin. The origin must be addressed separately. It is a dangerous point. Well, and we have here some sort of neighborhood. And the problem is that this neighborhood is not open. We would like it to be open, but it is not open because of the base locus. Yes, if at some point both f and its perturbation vanishes, then at this point this neighborhood will not be open. Now this must be corrected because we want to work on some open set. So we will take a Hornick neighborhood of this base locus. So here it is on the picture. The base locus is in blue, and we take here the horn. And we want that the horn will be flat at the origin. flat means here not in the sense of algebraic geometry, but in the most naive sense of the calculus. Yes, so it is defined by flat functions here, or equivalently for any resolution, this intersection with the exceptional divisor will be just 1 point. This is the flatness of the horn, and we will add to this u0 this horn to get a better neighborhood. So once again, we have the base locus of this family with with the erased origin. It sits inside u0, which is the total space of the family except for the origin, and this sits inside the germ of Cn, and we have the theorem. So there exists a small open neighborhood u of u0. It can be taken as small as we want. Sorry, it should be n here, not n plus c. And a flat hornic neighborhood horn, as I demonstrated on the slide before, the neighborhood of the base locus. And a trivializing isotopy, yes, the continuous map from the product of the germs to Cn and the origin, and with the obvious notation phi subscript t, with the following properties. So first of all, at time 0, this phi0 is identity. Yes, it does nothing, because t0, t equal to 0, you don't need to perturb anything. Moreover, for any t, this phi t is identity outside of this u. Yes, and remember that u is very close to the total space of the family, so basically we do not perturb anything far from the family. And the identity also on the base locus. Now phi is C infinity outside of the origin. Yes, the origin is always dangerous point and it will be treated below. Moreover, phi is real analytic outside of the boundary of this u and the boundary of the horn. Now, the boundary of the u is the real analytic hypersurface, and also this boundary is the real analytic hypersurface. And so you see that phi is real analytic everywhere in a rather strong sense. Sorry, not everywhere, almost everywhere in a rather strong sense. Moreover, phi t acts on this horn, yes, and when we restrict phi t to the horn, or rather to its closure, then we get a function flat at the origin on this horn. Now, phi t does its job. Yes, it moves the central member to the member at the time t for any t. Moreover, it does something much better. It moves every member of the family to some other member of the family. Yes, we start from some s, time s, and here is some other time. And this happens, well, except for the horn. Horn is the small neighborhood of this base locus, and it is problematic. But outside of this horn, which is rather small, phi t sends every fiber to some fiber. And here, this function tau t is a real analytic shift function. It just shifts the time. One more property, phi t lifts to the C infinity automorphism on the resolution. Yes. Remember, previously it was C infinity except for the origin, but upstairs it is just honest C infinity everywhere. And it acts on E, of course, because phi was preserved in the origin, so phi tilde must act on E somehow. And it is a real analytic outside of, again, the boundaries of the strict transform of the of the U, yes, and the strict transform of the horn. And here we have also the strict transform of the base locus. intersected with the exception divisor. And finally, the most important thing is the differentiability properties of this phi t at the origin. And they are determined by the multiplicities of the total transforms of all the defining equations and of the perturbations and of the local coordinates. There exist some very explicit formulas. And there are many other nice properties. So this is the theorem. It constructs the trivialization, once again, without differential equations. Essentially, everything is based on the implicit function theorem. Just one remark, in some cases, the base locus is trivial. It is only the origin. For example, this happens for curve singularities. It also happens quite often for surface singularities which are not hypersurfaces. So for surface singularities embedded with codimension at least 2. And then if this base locus is trivial, then we take horn just as empty set, and then the whole statement simplifies. Of course, you just remove horn everywhere, and the properties are even better. So this is the theorem. Now let's see some applications. I restrict only to the simplest applications. We want to trivialize, once again, I recall what we are doing. We want to trivialize some family. Yes, and we want that our trivializing homeomorphism will be differentiable enough at the origin. Let's speak about weighted homogeneous singularities. Fix some weights. As always, I order them without any problem. So all the weights are rational. And to take the corresponding action by weighted homogeneous scaling, as always. And take some weighted homogeneous polynomials. Yeah, so f, all the coordinates of f are weighted homogeneous. And here are their weights, some numbers, rational numbers. And suppose that this zero locus is a reduced isolated singularity. Not necessarily a complete intersection. Now take a pi-resolvable deformation of this isolated singularity. Yes, so again, first we take its resolution, call it pi, and then we take the pi-resolvable deformation. Well, and here are the weights. Of course, we perturb. This perturbation has its coordinates, and we record the weights. Assume that the weights are at least the weights of the initial function. And then corollary, that this family is C-R-lib trivializable, where R is determined very explicitly by this formula via the weights. Now, maybe to emphasize, so what this means, it means that trivialization is differentiable that number of times at the origin, and the R's derivative is Lipschitz at the origin. So, for example, if R happens to be non-negative, yes, then we get that the family is Lipschitz trivializable. Well, sometimes it is negative, and then we only get that the trivialization is continuous, which does not say too much. So this generalizes and strengthens several known results, because the question is quite old. Now, another application to curve singularities. So let's start from a reduced curve singularity, not necessarily a complete intersection. Again, take a resolution denoted by pi, and take a pi-resolvable deformation. Now, for this resolution, take the multiplicities of the total transform of all the equations and all the perturbations and of the local coordinates. And then we get that this family is CR Lipschitz trivializable, where R is given in this form. So once again, it means that trivialization is at least r times differentiable and the r derivatives of order r are Lipschitz. And now notice that in this case, we certainly have that this is non-negative. So r is at least 0. It means that the family is at least Lipschitz trivializable. Well, this generalizes and strengthens also some results. This is again very old question. So, for example, Farman, Tessier, and Fernandez. Well, my time is over, so thank you very much for your attention.